These days, what happens is if you have a comment, you just put it right in the chat while the presentation or the conversation is happening. What we're going to do today, as we said in the description, is to talk about physics not as that thing that people in school are afraid of or feels too distant or difficult, but to revel in physics as what it is. It's a way that we're trying to understand our world and our universe around us, and it's fun. It really is. My goal is to talk a little bit about physics, maybe a few recent discoveries, exactly, Raymond Helfrich, um, fun with physics, and I want to answer your questions. The book that this presentation is about is this one. It's called the Handy Physics Answer Book, and it's a third edition. The first edition was written by somebody who's now the superintendent of schools somewhere in Bergen County. Pascack Valley, I think, was a physics person. And then the second edition was written by a gentleman named Paul Zitzowitz, who is a great physicist in Wisconsin, who has also received a Lifetime Achievement Award from the American Association of Physics Teachers for his textbook work. And then I had the privilege of doing the third edition. And we talk about all kinds of things in this book, all physics. And if you have questions, this is the meat of today's program. Questions you might have about physics, not just like physics like, Newton and Galileo and Einstein type physics, but like the world. How do things work? What is going on out in the daily lives or in the universe itself that you have questions about? Get those questions ready. Think about them while we talk, and then enter them into the chat. Okay, put them into the group chat at some point. And then we will just go through them and we'll answer them and then we'll follow up. And the goal is to have fun. All right, so thank you all for coming and let's get started. Here's how I'm going to start. I will acknowledge to my disappointment that we physics educators suck. We have failed you in crucial ways. What do I mean by that? For 100 years now, we physicists are so enamored of ourselves to some extent that we feel like we belong to a secret club. We talk amongst ourselves, and then we obviously know cool things like how atoms work and how molecules and the shape of the universe and all kinds of crazy things like that. And then we deign to allow some students to come join us once in a while. But when you come in, you must speak like us. You must talk like us. You must do the equations the way we tell you to do it. And if you don't do it our way, well, then you're just not good enough to be in our club. Uh, and unfortunately, this pervades my entire group of colleagues. And I have found it very difficult, even for myself over the years, having spent lots of time and effort to become part of this club of physicists, to realize that I have caused my own problem. I've created a circumstance where you all think if you're not studying physics like crazy and if your brain isn't into it all the time, that it's not for you. So this book, the Handy Physics Answer Book, I wrote specifically to avoid that kind of talk. Everything that we tried to do in this book, and just in general now, is to tell people you are a good physicist. You do physics all the time, every day, and you do it well. The only thing is, you didn't do well necessarily in physics class. And that's because of us. It's our fault. So with that in mind, I would like you all to please keep that in mind. Anytime physics feels bad or difficult or distant, blame me. Look at me right now, right? Me. Yes. Yeah, my fault. cast those demons to me, or any other physics teacher that you didn't like, but I'll take the blame on behalf of us all. And now think about how cool physics is. Okay, so that's the step I'd like to start with, and let me tell you how cool physics really is. Uh, Modern physics started not with Galileo and Newton and so forth, but with people from thousands of years ago trying to do simple things. How do you get this heavy object up a hill? And by doing experimentation, they realized that, well, if you've got a block of wood and you push it up the hill, well, it's really hard. But if you put the block of wood on a cart with wheels, then it becomes a lot easier. Why is that? Physics is trying to solve problems and seeing how the world works. And that kind of innovation is what drove our civilization forward for thousands of years before anyone ever wrote down a single equation about what the mathematics of a falling body or an X-ray or anything like that was, right? Now, around 2,000 years ago, there was a guy named Aristotle that you all probably have heard of. And Aristotle wrote the first book that actually had the name physics attached to it. The idea physics, he spelled it with a K, of course, because the Greeks used the letter K and not the letter C for the K sound. He was explaining how objects moved. He's trying to figure out why things move back and forth, and how things interact with one another. The most important question was, why do things fall, right? If we jump up, we fall back down. If we throw a pebble over a cliff, it falls back down. Everything that goes up always came down. This was thousands of years ago. They didn't have other ways to get up, but that downness of everything was always so important. And so Aristotle came up with great ideas. Today we would call them hypotheses, right? Educated guesses about why things worked. And this is the beginnings of some of the philosophical underpinnings of what we consider as science today. So this was what he basically thought. I'm going to take some random object in this room here. How about this? This is actually a container of organic bone broth. What is this doing in my room? I have no idea. But let's take this object, and here's my hand, right? And what you do is you let it go, it always falls. Why is that? Aristotle came up with the idea that nature abhors a vacuum, right? There is a vacuum, he said. What we today think of as air, he considered just emptiness, right? The space between this container of bone broth and my hand is a vacuum. And so an object will always want to close that vacuum off because it doesn't like vacuum. So nature abhors the vacuum. And people were cool with that for a long time because it explained everything fine, right? Because you have the desire for nature to abhor the vacuum, the more vacuum there is, or the more stuff there is between you and this other thing, the worse it would be. And therefore, so if I had two of these things, all right, and I tied them together in a bundle and they fell, then they should fall twice as fast. This is what Aristotle said. These were some of the examples of the conclusions that philosophers like Aristotle made based on their hypotheses, which is what we consider their good ideas. Along comes a guy named Galileo. Okay. Now, I go to Galileo in part because I'm partial to that individual and that name and the role that Galileo plays in history. However, really, there is a lot of people, there's a whole stack of people that we don't learn about in our history usually that contributes to the concept of science. One that I'll mention right now is a gentleman named Al-Hasan, okay, who lived in Basra, modern day Iraq, who during the period of the caliphates did a great deal of scientific work and wrote a lot of things about that. He also spent time in Egypt in his adult life. And he wrote about this concept that not only should you come up with good ideas and make conclusions about what those ideas were, you also had to test them, right? So, oh, if you actually have a rock that's twice as massive as some other rock, you should drop them at the same time to make sure that the heavier one fell faster. If you didn't test it, then as good as your idea is, you can't use it. It's just an idea. You have to test it to show the case. That's the basis of what we call the scientific method today, right? And so Ahhazen, hundreds of years before Galileo, came up with that. And then there's another gentleman named Sir Francis Bacon, who also came up with this idea later on, possibly independently, possibly after reading some of the texts that had been brought back to Europe after the Crusades. But the idea that in order to make something true, to know that it is the case, you had to test your hypotheses. Galileo, what he did was he tested things and he observed things, but in such a way that he made it very public. He might have been the very first Carl Sagan, the very first Neil deGrasse Tyson, the person who not only did the work, but also told people about it. This is another one of those things that I criticize myself and fellow physicists and scientists about. We are trained to make discoveries. And then once we make discoveries, we publish them in journals of repute. And then we talk amongst each other as we read those journals. And, that's pretty much all we do. We just keep generating materials, more and more new information, and then we just let people read it. But how does that benefit the world? Someone has to take that information and bring it to the rest of us, right? Teachers or educators of various kinds, popularizers, or you just take your time to actually tell people about it in language that they can understand. And so that's what Galileo did. He wrote about these things. He wrote about dropping objects of different masses from the same height and finding that they all landed at the same time. Why is that? That doesn't seem to make sense. That's counter to Aristotelian ideas that had lasted for thousands of years in Europe. But that test showed that Aristotle was wrong. Now, is Aristotle bad because he's wrong? No. Another thing that we scientists are guilty of in our classrooms, to all of you, and feel free to raise your hand or to put something in the chat if you want to. If you guys all know how to raise your hand, you hit the reaction, right? You can tell me whether or not a teacher actually spent time and effort to tell you what was cool about what they did. Or did they just have you do stuff to figure out the right answer? Were you evaluated in your courses as for the questions you asked or for the answers you gave? And if you only gave answers, were you, say, devalued or considered to be lesser if your answers were wrong than if your answers were right? Right? Any of you had any of these experiences? You can raise your hand. You can put something in the chat. You can use a reaction button. That's exactly what we do in our educational system today for science. And it's been that way for a century, maybe centuries. It's terrible. Sure, we want to get the right answer, but if we think about things and we try hard and we get the wrong answer, that's way better than not giving any answer at all. Even better, the most important thing is not getting the answer, but is to ask the right question so that when the answer comes about, it becomes meaningful to us all. And so Galileo did precisely that. He did physics on the Earth by dropping objects. He rolled things down inclined planes. He did all these sorts of things on the ground. He had even created a thermometer back in the day before people really understood how temperature worked. But he also did physics out in space, right? And this is long before any of us get out there. Um, you can imagine that people in the 1600s thought that space was unreachable, unattainable, that it was nothing like Earth. But what Galileo did was he heard about this discovery, this new invention called a telescope that could make objects far away look closer. And so he went to, at that time, his head of state, the Doge of Venice. He was already well known as a writer and a scientist at that time. And he went to the Doge of Venice because Padova, where he was within the control of the Venetian city-state at the time. And he said, look, these telescopes are really cool. I will build some for you if you give me the money, and then you can station people up in the buildings and out in the outer islands in the Adriatic Sea and look out there as an early warning system in case ships were coming in to attack. Doge of Venice was like, oh, that's a great idea. And so funded Galileo's telescope making enterprise. This may well be the first documented example in the European history of having science be advanced by defense funding. This military funding, which protected Venice, also allowed Galileo to build additional telescopes, which he used to look up into the sky. And in 1609, he published a book called The Starry Messenger, where he drew pictures of mountains on the moon, the phases of Venus, moons of Jupiter. He showed that the planets, instead of just being mysterious gods or dots of light in the sky, were actually worlds just like ours. He showed that we could walk on the moon, just as if we were walking on Earth. These were places we could go, and they must follow the same laws of nature, the laws of physics. This was very controversial at the time. Galileo was criticized heavily by many, many people. And before the ultimate criticism, when he was brought before the Inquisition and forced to recant in public what he wrote and what he said, before that, people were saying, nah, this Galileo guy doesn't know anything. He's just being goofy. And anyway, if you see an object through a piece of glass or through several pieces of glass, you're not looking at a real object. You're looking at something that's been altered, that's been changed. So it's really just an image. It's an illusion. It's not reality. That doesn't count. Whatever you see out there, nah, we don't believe it. And he was roundly criticized for these things. And he said, well, you just say these things, but whatever. And so finally, he wrote a very, very meaningful book called Il Saggiatore, The Assayer. Let me type it into the chat just so if you ever want to look this up on the internet, you can do that. This is the book by Galileo Galilei. Like that. When you say something like, well, as Raymond is saying very nicely, I like the way you think. That's not what I was looking for. That's how you should answer every question. And what Galileo said to the following was that he said, there is no right or wrong unless you actually have proof. Go out and do it. Go out and look at it. He said, back then, philosophy was like, what is the beauty of a tree? right? What are the ethics of rocks or the world? They were trying to use philosophy to establish an understanding of the whole world. And it wasn't working. They were hitting a point where people like Galileo, who were making observations and experiments, were being attacked because they didn't have the ability to tell the others who were saying, well, that's not beautiful. That's not ethical. That's not moral. That's not part of philosophy. Right? So, in this book, The Assayer, Galileo wrote the following. He said, it is now time to have an understanding of the world that is independent of philosophy, but dependent upon empirical observation and investigation. In other words, there is now a world which is tangible and which you can do things with, that the truths of this world come from experimentation, come from observation, come from actual things you see and notice, as opposed to those other things in philosophy that, is there or it's not. Eh. Uh, but it's like deep and it's thoughtful and it's beautiful and it makes sense. So that kind of philosophy got separated off, kind of sort of into the arts, into philosophy, into aesthetics, whereas this empirical stuff became known as what we call natural philosophy. Today we call that science. Right? That kind of split had both good and bad to it. Good because it meant that you could, in fact, figure out properties of rocks and trees without wondering whether or not they're beautiful or whether or not they're ethical. You could actually do things that experiment and then you could build upon this method of asking questions, coming up with educated guesses, hypotheses, and then testing them to see which was right or which was wrong. And if it was right, then build on it some more. And if it's wrong, fix it and try again. That kind of method of learning stuff. Now, today we call that the scientific method. That gives us what we have today, our technological world, in so many ways. The problem, of course, was that when we separated, the separation in some ways was too sharp. And today, how many of you hear that, oh, well, if you do physics, you can't do art. If you love math, then you surely must not be a musician. Things like that. And we know that that's far from the truth. All humans can do math and science. But what happened was the people who happened to like the arts were then told, well, you're not good enough to be one of our scientists unless you actually speak our language, talk the math or talk the science. If you don't know all of our words, you don't count. You can't be in there. And so this exclusionary idea of physics has come about, and it's really unfortunate. I know that there's Jeff the opera fan is on. I wanted to use opera just as a thing because the reason I love opera. Okay. When I was in college, I had learned up to that point almost nothing about opera. But when I went to college, I was at the radio station at the college, and I said, I want to do a radio show about opera. I want to do this show that was on once a week that was about people who were great singers and like Caruso or John McCormick or Victoria de Los Angeles and all these wonderful people, Maria Callas, and play their arias and learn a little bit about it, and because it's so beautiful, it's music. And the opera buffs in the radio station folks said, you can't do that. You don't know opera. It's like, I'm like, well, I can learn. And they said, yeah, well, you'll have to pronounce all the Italian names of all of the operas and all the arias correctly. You need to know when they were done. You need to know the names of these singers, and you need to know all those things cold. You just have to do that. Otherwise, you can't do this show. And I was like, oh, man. Fortunately, my ego was the size of the Empire State Building, and I refused to take no for an answer. So I did it anyway, and I received great castigation unfortunately, from some of the people there, but I didn't care. And in fact, I had a good time, and there were plenty of listeners out there who like enjoyed it with me. So in the end, the naysayers I didn't have any problem with, but they were naysayers at the time. And to this day, there were there are people who are like that. Well, if you can't recite, all the Valkyries names in, the ring cycle, well, then you're just not part of our club, that kind of thing. And a person named Greg, who knew opera colder and better than just about anybody I know, was the person who explained to me when I wanted to do that Great Singers of the Century show. Don't worry about those folks. If you love opera and if you love singing, just do this show and that'll be fine. So today, decades later, I still love opera. I'm really glad that Greg told me, don't worry about them. It's all good. And I want to do the same for physics for you all. And so if you have any inkling, interest in how the world works, I want you to like that physics. Just like Galileo pushed the envelope. Just like Greg helped me push my opera envelope. If you think about how the world works, I want you all to leave today saying, I am a good physicist. I may not be able to write down the equations for a test. I may not be able to tell you that if I hang a string over here and I put a pendulum over there and I put a bar of metal in this direction, how fast will it swing for how long, right? I can't tell you that today, but I'm still someone who likes physics and cares about how the world works. So with that, I will stop for a moment, okay, and ask you all to start putting your questions in. I see many of you have already been putting things in the chat, and I really appreciate that. Oh, Raymond, thank you. You said you just bought this book. That's very kind. But anybody else, whether or not you buy the book, really, it's totally okay. The questions that you might have, the people, things that you might want to have answered, is now the time. So start entering things into the chat, things that you might want to know, and we'll do some Q&A for a little while. Then I'll go back and talk a little bit more about physics later in a little bit, okay? And also now, any of you who've been sitting for a little bit too long, now is a good time to do what I'm doing, do a little bit of stretching, stand up, lean back and forth a little bit, make sure that your muscles are good. If you can, look at something 20 feet away for 20 seconds, just so you can have your eyes back and forth and relax and contemplate the physics of the universe. All right? All right. Oh, this is one of those few advantages of all this distance stuff. You can get up and do whatever you want anytime you want to, right? Okay. So let me try to answer a question. Here's a first question. What is string theory in 10 words or less, and has it been abandoned? Oh, it's great. We're getting right into the meat of everything right away. Let me bring a few more questions a little bit further. Let's see. Mindy asks, can you explain gravity, how it impacts space-time, and why time moves slower and faster? Good. I have a private question. Are there everyday examples where we see physics in action, even if we don't know it, that I can mention? I certainly will do that, and I'll be happy to do so. And Joanne has a question, a comment, I guess. I used to do this experiment with sixth graders, let a pencil drop and a ball of paper drop at the same time. They would all claim that the pencil landed first, but no. How could I have convinced them otherwise? Let's bounce off with that question right away, Joanne. And for the rest of you, if you have more questions, please by all means jump in. Let's do that experiment right now. Here's my pencil, and I'm going to take a piece of paper from my recycle bag, the back of the envelope. We can do a quick calculation on the back of this envelope if you want to. All right. So which one would fall first, right? Obviously, if you drop them now like this, they should all both fall at the same time. But the people all claim that the pencil lands first, right? But actually, they fall exactly the same speed. How do we convince the sixth graders that they're not right? Have them drop it themselves. Bring a sixth grader up who is a naysayer. and say, here's a pencil, and here's a crumpled paper. You drop it. You make sure that you drop it in such a way that it's as fair as possible. And if everybody does it, and everybody sees, oh my gosh, even as I drop it, it still lands at the same time. Surely uh, I was wrong before. Does that make sense, Joanne? Having
Certainly, I'm going to respond actually verbally here, because it was always very interesting to me that they refused to see what was in front of their own eyes. And you're right. I mean, that's what I did. We just did it and did it and did it until finally they're like, wow, well, maybe that's right.
uh-huh, right. And another thing to do is to change your object. Take a pencil, take an eraser, right? Or take a pencil and take two pencils tied together with a rubber band. As you're dropping different objects, people think that paper flutters to the ground, right? But people won't think that two pencils should fall any slower or faster than one pencil. There is definitely a thing that happens, right, with the air resistance that sort of bounces. And as a result, you wind up with different speeds. But our idea of what friction does, or air resistance, or what we call viscous drag, right? It depends on the thickness of the air. It depends on the viscosity of things, right? If you're dropping different things at different speeds, it depends on the air. It depends on the cross section, how much area is falling down compared to the other. All those things matter. And it turns out that in the simple dropping experiment in our daily lives, those effects are sufficiently small that you're okay. Now, if you took a piece of tissue paper and dropped it with it, it would flutter to the ground in all likelihood, and you could tell that there was a difference. But
Yeah.
take that piece of paper and then crumple it, and then see what happens. Then all of a sudden, because the area is smaller, you wind up with a better situation.
And
So,
ultimately in that, and I'll leave you with this, is we did it with a crumpled up piece of paper, and then I had them uncrumple it and spread it out and did it. And then it was obvious that the pencils hit first. So
brilliant. Joanne, you count as one of the awesome teachers. Yay! 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 Woo!
good time. We had a good time in science.
Oh, we as kids were asked about a pound of feathers and a pound of stones, and
Right.
that's confusing, feathers and stones. So which is going to drop down first? They
Right.
both weigh a pound, so they're both going to go down at the same time.
That's right. If it's not a trick question, as some of these sometimes are, Jennifer, if it's not a quick trick question, they should fall at exactly the same rate. But feathers, of course, has a big surface area compared to how massive they are. So if they were just out by themselves, they would flutter. But if you tied them all into a bag of the same size, so you'd have to compress the feathers down into the bag, right? And then you take the pound of other heavier material and they're the same size, then they would resist the air at the same rate. And so they would fall at exactly the same amount. It's only because of our idea of individual feathers as opposed to a pound of feathers. The trick question, of course, is, what weighs more, a pound of gold or a pound of feathers, right? The answer is a pound of gold has troy ounces in them or something like that, or an ounce of gold weighs different amount than an ounce of something that's not metallic, or something that's not gold, because they don't measure it in the same kinds of ounces. But those are the kinds of things that we trick ourselves with, that sort of thing. So let me get to some of these questions now. There's so much. Oh, an ounce of scotch. Yeah. Pour an ounce of scotch down. I think that goes faster than anything else, especially under the right circumstances. So let's get to that string theory thing. Let's start right away with this big, heavy thing about the universe. The universe, as we see it today, as described by Galileo hundreds of years ago, has length, it has width, and it has height, right? 3 dimensions of space. When we look very, very closely into the atomic structure, and I'll talk a little bit more about this later, of the universe, and we look at the tiny, tiny particles, we find surprisingly that if you only describe them as objects that have length, width, and height, in other words, the only kind of way they occupy space is by these 3 dimensions, there are some unexplainable phenomena that occur. things that we think should happen. If you had like a rubber ball or something, or if you had a brick, or if you have a house that's three-dimensional, that would work completely in our normal understanding, fail at the smallest levels. And so it has been hypothesized that there are even more dimensions that we cannot see, that somehow rolled up in length, there are three additional directions. There's like a length and a length width and a length height kind of thing. And then there's a width and a width length and a width height. And there's a height and a height length and a height width. You know, extra dimensions that have been squeezed into the dimensions that we have. In that case, these objects aren't so much three-dimensional solid objects, but each of those little particles is coiled up like a spring, or many springs, like a string within all these different things, kind of rolling around. And when those strings are interacting with one another in dimensions other than our length and our width and our height, some of those unexplainable phenomena are then explained. It's a cool mathematical structure trick that actually still works in many ways. But the problem is, you can imagine, it's very hard to prove. Remember Galileo's basic step, where you have to do some sort of experiment, some sort of test to show whether or not your idea is true. String theory works in many ways mathematically very well, but so far our ability to test it has been limited. And some of the tests that we use, for example, whether or not a proton actually decays, that so far we've had null results in our experiments, despite all of our efforts over the years and the decades. So that question remains. And it's one of the real fundamental ideas of what's there. All right. So that was way more than 10 words. I'm sorry, but it has not been abandoned. It just keeps having to be worked on. All right. So, wow, so many great questions. How about, oh, this is a really good idea. An educator suggested, if you want to, these days in the 21st century, do that experiment that Joanne was talking about dropping things like a paper or pencil and so forth, and figuring out which one falls first. And if we don't believe ourselves, we have cell phones these days that take really good video. And this educator suggests putting a phone or an iPhone, having a student. Oh, wow. Imagine students being able to take out their phones during school. That'll make them excited, right? That makes them happy. Take the phones, have them record the video so that everyone drops it, and then they can pull the video back and scroll it and see what falls down first. What a great idea. That's 21st century thinking. There you go. Yay for that educator. Woo! Woo! Yes! Oh, this is great. That's what I'll do in my physics class this semester, I think. That's what I'll have to do. Okay. All right. So let's go back to the arc of the history of physics, which will then lead to answering some of these questions, and then get to the frontier again about gravity. Okay. And to talk about these things. Here we go. After Galileo figured out that it was all about motion, movement back and forth, and how things move, it was back to Aristotle again, right? Aristotle said things move for a reason. But now the reason that Aristotle said that nature abhors a vacuum was disproven by experiments. And what Galileo said, that there had to be something, a push or pull, that made things move. Isaac Newton, who was born the year Galileo died, and some say that there's been no more symbolic passing of the baton in the history of science anywhere. Isaac Newton used math to explain what those pushes and pulls were. He said the push or pull is known as a force. And what force does is it changes the amount of motion of an object. The amount of motion of an object is a fundamental property of any object at any given time. And he called it momentum. So force changes the momentum of objects, which makes them either speed up or slow down or change direction or some combination. Okay. And so he used force and momentum to explain all these things. Now, here's the problem. Explaining force is not super easy because you're talking about how something changes over time, right? So if I know that this thing, let's say this thing had a value of 2 1 second ago, but it changed and now it has a value of 1, right? That means that over 1 second, it changed by -1. Oh, now we're starting to talk math. We're starting to talk rates of change. And the math had not been invented yet to talk about rates of change effectively. And so Isaac Newton invented it. And I think most of you know what the mathematics about changing rates is called. It's called calculus. Now, calculus today also intimidates people. They're like, oh my gosh, you're taking calculus, right? Actually, calculus is not that much of an obstacle, no more than physics is. But it is a different language. Galileo himself was quoted as saying, mathematics is the language with which God has written the universe. So in the same way, for example, that if you want to get a joke in French, you really kind of ideally should be able to speak French, because once it gets translated to English, the punchline kind of gets lost. So learning math is valuable if you want to understand physics, because it's a language. But let's say you're not fluent in French. A good translator hopefully can still translate the joke well enough that you still laugh, even if you only speak English. And that's what physics is like to a lot of us. We do physics, but we need someone to translate it so that we get the joke. So what Newton did was he made the math and he figured out the force and he figured out how all that sort of interacts with one another to understand how things work. Great. So far, so good. Time goes by. We have things moving around in the sky. Galileo showed that they were objects, worlds just like ours. Isaac Newton showed that they move just like us. So gravity is a force, he explained, that moves things around. Gravity is a natural force that results in a pull between any two objects. The further apart they are, the weaker the pull is. The more massive they are, the stronger the pull is. And there's a balance. And when you have a perfect balance in the motion, you get orbits. You get Earth going around the sun, moon going around the Earth, moons of Jupiter going around Jupiter, things like that. So far, so good. That's motion. But wait, there's more. There's light. It turns out that light doesn't have any mass. What is that supposed to mean? The energy of light somehow must be transferred to us, even though it's not massive. It has to travel through space and time, but unlike me throwing a ball or shooting a dart or something like that, there's no object to move it. The piece of light is something that has no mass. All it has is something else. Obviously it does something, right? It carries something, because if it hits us, if it hits our eyes, it reacts with our eyes and we can see things. So that thing is energy. It turns out that light is a form of energy, and that moving objects contain a form of energy. Falling objects contain a form of energy. A chocolate bar contains a form of energy. When we eat the chocolate bar, the energy changes into a different form. It's amazing how this thing, which has no mass, somehow affects us all the time. and things that have mass carry this energy around. That carrying of energy and how it goes from place to place was taken to the next level by a guy named Hamilton. Not Alexander Hamilton, William Rowan Hamilton. Now, this is somebody that actually, if you watch YouTube and so forth, there's some very whole bunch of these young YouTubers who got together and put a video together using the Hamilton music to talk about William Rowan Hamilton, who was a mathematician and a physicist who explained that you could take the energy of objects, and by using energy, you could explain things like forces and momenta and systems that otherwise couldn't be easily described by just stuff that happens to be moving, things that you push or you pull. So now you have Hamilton, and then gravity starts getting messed up. Gravity, of course, isn't messed up in the mess up, but this is what happened. By 1900, people were pretty good about figuring out things like heat and light and motion and things like that. They thought they kind of understood what was going on. And around the turn of the 20th century, from 1900, 1899 to 1900 or so, some of the famous scientists of the time were saying, we're pretty much really good about physics. We just a couple of odd clouds in the horizon. We see how the universe works now in the motion, but there are some clouds that seem to be sort of moving in the direction. They kind of block the sun a little bit. Now, if we can figure out what those clouds are, then we might be able to solve how the world works. A famous scientist, William Thomson, Lord Kelvin, he was one of the first people who laid down submarine underwater cable to allow telegraph and telephone to go underseas and from continent to continent. Very wealthy man. He was given a peerage, so he became William Thomson, Lord Kelvin. And Mr. Kelvin, or Lord Kelvin, he gave a lecture and he said, there are just two clouds that I don't quite understand how they work. One is this thing about light, and like, how does light travel if it doesn't have any mass? What does it get carried by? And then the second was this question of, aside from light, sometimes when you're looking at objects, really, really small objects, they don't seem to follow the laws of physics. What is the deal with that? We said, these two things, if we can figure these things out, we're pretty good with science all the way. I think we got physics down pat. Well, it turned out that those two little clouds that he saw, that he presciently saw, opened the door for the entirety of 20th century physics. And we'll start with that gravity question, right? How does gravity impact space-time, and why time can move slower and faster? What happened was that Albert Einstein took some equations that had been observed by two other scientists, a guy named Michelson and a guy named Morley. They had measured the speed of light, and they couldn't quite figure out, their experimental measurements were very, very accurate, but they didn't follow regular physics. Instead, it seemed almost as if either the light was traveling slower in one direction compared to the other direction. Sounds crazy, right? Or it seemed to somehow like the Earth was shorter going in one direction compared to the other. That was so strange. This physics, it wasn't measured right. So what Albert Einstein said was, the reason your experimental results seem wrong is not because your experiments are wrong, because we checked your experiments, they look great. The reason is our understanding of physics is incomplete. We always thought about length, width, and height as being things, dimensions that we can move back and forth in, right? So we can move left or right, or we can move up or down, we can move forward or backward. But time just keeps on ticking, right? And time was always the same. What Albert Einstein explained was that no, time is also a dimension. So length, width, height are joined by a fourth dimension called time. And so space-time became a word. And this is Albert Einstein's theory of relativity. All right, his general theory of relativity specifically talks about the linkage of space and time as a four-dimensional structure. And so we live not just in space, but we also live in time. And just as you can change speed moving left or up or forward, you can also change speed moving through time. Sounds amazing, right? I mean, if I run really, really, really fast, will I experience less time than you? Will I actually age less than you? In the same amount of time that you age, maybe I age a little less? Amazingly, that's what Einstein predicted. People are like, you're nuts. This is crazy. You know, my friend over here, the world-class sprinter, he hasn't aged less than me. Einstein said, test it and find out. And with experimentation over the years, it was shown indeed, holy moly, it's true. It's almost imperceptible, right? But it's there. So if you take a plane, someday we will all, again, take planes. If you take a plane, just a regular, you know, United Airlines or whatever, from New York to Los Angeles, and then come back, if you were able to measure your aging very, very carefully, you will have found out that actually you have experienced a tiny fraction of a second less than someone who didn't make that same trip because you were moving. And during that time you were moving, you experience a shorter amount of time. It's amazing, but it's true. Unfortunately, that fraction of a second for such an intercontinental trip there and back is like 0.000000000000001 second. And whatever benefit of longevity you might have gained by that will almost certainly have been canceled out by the airplane food. What are we going to do about that? Yeah, for us, not so much. But for subatomic particles, for little things, that difference in time matters a lot. Today's modern computers, for which fractions of a second matter. Today, when we're using the GPS system, right? Because when those satellites are moving around in space, they're also moving in time, right? So as they move in space-time, Earth has been bending space-time. And so the gravity of Earth actually is changing how time is being experienced by GPS satellites. So to answer that question, how does it work? It's because space-time is affected by matter, which changes how things move, how things experience time and space. And so GPS systems have to continuously compensate for their motion in Earth's gravitational field. Otherwise, a few weeks after launch, it will think you're in the ocean when in fact you're on the shore. So it's that amazing difference that matters on a daily basis. You know, we don't think about anything. We turn on our phone, we say, you know, get us to the grocery store. We probably know how to get to the grocery store by now. So, you know, say we're driving to a friend's house or somebody that we've never met or a new location, a hot restaurant somewhere, and we're driving there and it tells you go here, go there, go here, go there, because these satellites have you pinpointed in position to within a car length of where you actually are on the surface of the Earth. But without the corrections for gravity and time and relativity that Albert Einstein explained, you would not make it. You would wind up probably in some parking garage, you know, saying, hey, wait a second, where's the restaurant? So it's really kind of cool how that's worked. So that's one of Kelvin's strange revolutionary points. The second point, which he said was a cloud in the horizon, something that, you know, we should be able to solve, turned out to be the idea of quantum mechanics. And this is the string theory thing that was mentioned earlier. String theory is the next level attempt to figure out how the physics works. So when we have atoms and molecules, you've seen these things in cartoons or on the side of a fallout shelter or something like that, right? You have this nucleus in the middle, and then you have these swirling electrons around the outside, the atoms for peace symbol, right? And you've seen that many times before, of course. It turns out that that structure of the atom was very controversial. It took a long time to figure out. And it's even more amazing than you think. Around 1901, a New Zealand-born British subject named Ernest Rutherford eventually did a lot of his work in Canada as well as the UK. He tried to figure out the structure of these atoms. And what he did was he used a generator of particles to shoot particles at atoms, like a thin sheet of atoms, and tried to fire atoms at it just to see what would happen. Presumably these particles would like scatter off, right? Bounce off these atoms. And then you could tell from the bouncing off pattern what the structure of the atom was. And what he found out was that if you fire 1,000, 10,000, 100,000 particles at these atoms, the vast majority of them, 999 or 9,999 or 999,999 out of a million, would just fly through and just hit the other side as if they hadn't encountered any object at all. But that 1 in a million or 1 in 10,000 would bounce right back. It was as if, it was said at the time, you took a cannonball and you fired a cannon at a piece of tissue paper, and the cannonball bounced off the tissue paper and hit us in the face. How can atoms do that? The only answer is that the nucleus in the middle, that thing in the middle of the atom, which contains more than 99.9% of the mass of the atom, occupies less than 0.1111 0.000000000000001% of the volume of the atom. Which means that what I'm standing on right now is basically empty space. Solid matter is almost complete vacuum. That is an amazing thing. Nature doesn't abhor a vacuum. Aristotle was way off. Nature is made up basically of vacuum. It is said that after Ernest Rutherford came to this discovery and this realization, he was afraid to get out of bed the next day. Maybe he would just fall right through the floor. For matter to be like that, there is no way that matter actually in our daily lives is locked together in such a way that we can stand on it and bounce off of it. Matter is way too sparse for that, which means that our friend energy is back into the equation. Somehow that matter is generating energy. Just like if you put a magnet in an opposite pole, same poles together, the opposite pole, north and south, they stick, but when you have a north and north together, they push away. There must be something in the atom that pushes away, even though it doesn't have the matter there to do it. So in our daily lives, this concept that you had to have mechanics, the motion of object, not necessarily touching, but just influencing one another through their force fields, through the energy that they generated, became born. And that is the root of quantum mechanics. And so now today, every time you use your cell phone, indeed, in fact, you'd look at me right now, right? There are things that are happening in your computer, in the chips, in the screens and so forth, that are happening because of this strange, quasi-solid, semi-gaseous, strangely vacuum-like structure of the atoms in the universe. Today, why can we use our phones? Why does this computer work? Why does the internet work? It's because of quantum mechanics. In our daily lives, this very, mathematically complicated thing is what enables us to be here, you and me together today. Examples of that kind of advanced science in our daily lives happen all the time. I don't know if any of you are electricians, but when I um, turn on a light switch in my house, um, if I spend a moment and think about it, I realize that what's happening is that there are electrons, little tiny subatomic particles, moving by the trillions through my house, along the walls, in the wires. Each room and all of the stuff behind it that allows me to turn on my laptop and turn on my lights and turn on my television, all of that is pushed around, electrons moving through wires that allows all of that energy to be created. It's such an odd thing to think about how powerful electricity is on a quantum mechanical level. It is billions upon billions of times more powerful than gravity. Right? If you just took a thimbleful of electrons and you put them at the bottom of a rocket like a Saturn V, unless there is an equal number of protons or positive charges to cancel that out, just that electrical force would be enough to prevent the rocket from launching. So electricity, even though it's commonplace, it feels so amazing. The math can be challenging. People who are taking electromagnetism, for example, and understanding how they go, well, sometimes calculating that stuff is complicated. But it's not any harder than writing an essay. It just happens to be not the language that we normally speak. But in everyday life, it's there. There's quantum mechanics, the nuclear forces. There's so much more to talk about that we can't even barely touch upon them. But the everyday physics, so much here. And I'll stop there and take a few more questions. I'm just got to go through these questions here. This is a very interesting question. Is physics motion and movement like the market? Stocks go up and down and sideways. Algorithms, physics, quantitative analysis. How close are they to actual physics? Great question. Almost all of the automated computer trading in the stock market that you hear about today, that you see that the high rollers are supposedly doing to make money, just about all of those algorithms were written by physicists. Started about 30 years ago, and today one of the most lucrative things that a physics student can do is to go to Wall Street. Because the way that you try to predict the motions of different products, or the way that you think something correlates with another, whether if this goes up, does that also go up? And therefore, can you make money off of it? All those things are ways of analyzing the motion of particles or the overall transfer of energy from one system to the next. So when people said, you know what, we can try to treat the stock market like a system that we can model, we wound up wanting physicists to make those calculations for us. So at least one, I think two right now, of my class, PhD students who we got our PhDs around the same time. Two of them went to Wall Street, and they are really, really successful. And they loved their science and their physics, but in the end, it was the way of thinking that led them to their careers, and their education was preparing them for that kind of concept. Okay. Here's a good question. Joanne, the awesome sixth grade teacher, right? I have heard that when I sit in my chair, I'm not actually sitting in my chair. I'm elevated an infinitesimal amount above the chair. Is there truth to this? Right. This is exactly what we were talking about in the sitting of the chair, right? About the force fields between the subatomic particles. And what I will say, Joanne, is although, yes, we are, you could say that we are a tiny, tiny bit above the chair. A better way to say it is that you actually are in contact with the chair, because the chair isn't just its solid parts. the chair is not only its parts, but also the field of energy and force that its particles have produced. So we are also this sort of strange amalgam of matter and energy. Particles can be treated as waves. Waves can be treated as particles. This is a fundamental aspect of quantum mechanics. It was put together by a gentleman in France. His name was Louis William de Broglie, Debrogie. So sometimes people learn him as de Broglie, but he's de Broglie. And he was able to produce this fascinating idea that we are both matter and energy, that we are both waves and particles all at the same time. So it's a profound and interesting question, not at all strange, and it makes a lot of sense. Okay, is glass a liquid? Ooh, let me mention right now, I think I'm down. I've covered all the questions that are up in the page now. So if you have more questions, now's the time to add them, okay? Because we're here for a few more minutes. We're kind of technically wrapped up. This can be sort of the last question, and then people can, if you need to go, you need to go. It's totally fine. We're here till about 8 o'clock. Is glass a liquid? That's a great question. The answer is glass is a solid, but it flows like a liquid. See, when we think of solids and liquids and gases, it's the way that the particles in the material move compared to one another that determines their state of matter. Okay, this whole process of what is solid and what is liquid and what is gas depends on the amount of what we call entropy per unit mass. And if you are trying to go from an object where the different particles can only sort of vibrate relative to one another, but don't actually slide loosely to one another, that's one state of matter. If you inject enough energy into it, the entropy per unit particle or entropy per unit mass increases enough that the particles start sliding back and forth, and that's a liquid, right? Now, as it is going from this state to that state, though, it can have an intermediate ability to do some of the things that you would expect of one state of matter, but not of the other. So there's like this strange mix point where a solid can behave like a liquid. There's something called a critical point where a liquid can behave like a gas. All of these things are a really cool part of solid state physics, which is not my specialty, but they're allowing things, for example, like solid materials. If you've heard of superconductors, solid things like trains, to be able to interact with their train tracks in such a way that they really don't touch, that they're only pushed apart, because at a superconducting level, the friction that is ordinarily created or caused that prevents, say, things from moving without friction or electrical resistance is reduced to nothing, which allows you to just zip on by and do some crazy things. So, all right, let's find a couple more questions here. Why do the magnetic poles on Earth move around? Ooh, good question. Although the specific geology of it is not my specialty, what I can basically say is the reason the magnetic poles on Earth move around is because Earth as a magnet moves around. Earth's magnetic field is created primarily by the liquid metallic part in the core of the Earth. When you have something that can conduct electricity, like a blob of metal, it doesn't necessarily have a magnetic field until the metal starts to move with relation to some electric current. Okay, so what you happen in that case is that if the Earth and its core, which is, has this liquid portion to it, were always perfectly aligned, they were exactly the same, then if the Earth tilt this way as a whole, then the magnetic field would also tilt that way as a whole. The liquid part would tilt the same as a solid. But since this liquid part moves relative to the top part, you can have these kind of strange gyrations or rotations and things like that. Okay. And so that is a function of the fact that the Earth is a complicated system. It's held together by gravity, but a lot of things are still moving around. And the Earth is only about 4.5 billion years old. There's still a lot going on inside. Not that 4.5 billion years is a short time compared to our lifetimes, but compared to what the universe can do, it's a pretty long time. Okay, pretty short time, excuse me, I should say. How can I slow time down? Which seems to go by much faster than when I was younger. The answer is you cannot slow time down in general, but you can slow down the amount of time you experience compared with somebody else, depending on how you move relative to the other person, right? I'm pretty sure that the reason we feel today that like a year goes by much more quickly than a year did when we were, say, 6, is because at age 6, 1 year is 1/6 of our lives. Now, at our age, 1 year is much less than 1/6 of our lives. So it feels like a shorter time, but there is just the same number of minutes, same number of seconds in general. So the so-called twin paradox, Leonora, is the one where you sit in a spaceship and here's your twin here, staying here on Earth. You get transported by this spaceship very, very, very fast. And then you come back around and you land back on Earth. You went very, very fast away and then very, very, very fast back. And you return, you have aged only a few years, whereas your twin has aged many years. That's how you can slow things down for yourself. The big challenge is to figure out how you can enjoy that amount of time or experience it in a way that's as meaningful and compact, full of good stuff as your twin who has been experiencing during that whole time. That is something that we haven't been able to solve the question for. Okay. Oh, we have someone trying to quote Rent, right? 525,600 minutes. That's true. How can Benford's law be found in physics? I recently learned about the first digit law found in many facets of life. Benford's law is really interesting. What happens with Benford's law is that, like, if you just grab a whole bunch of numbers, okay, usually the leading number, that is, the first digit in the whole number, tends to be small. It's a weird thing, but it's kind of true. Like, it turns out that the way you pick your data sets actually matters to make it that way. But it does happen that for some reason, if you just take a gazillion numbers, picked just the right way, surprisingly, the first digit is more often a 1 than anything else. And it's more often a 1, 2, or 3 than 4, 5, 6, 7, 8, and 9 put together. How does that relate to physics particularly? Not sure. I don't know. It is kind of interesting, but I'm not really sure why that's the case for physics. Because with physics, numbers are arbitrary, right? Think about this. If I declare that this ball of paper, which I dropped earlier, weighs 10 ounces, you'd say, no way, that's not true. This thing probably weighs 2 ounces. And you'd be right, because an ounce is something that's been defined before. But what if I said that this thing weighs 10 blurps? Well, what is a blurp? A blurp is 1/10 the mass of this object. So if this thing is 10 blurps, then the number 1 shows up at the beginning, and so Benford's law seems to take hold. But what if I said this is 9 blurps, and I declare that this is 9? Then all of a sudden it doesn't hold, because I have defined what the units are in the measurement of the mass of this object. And therefore, it is up to me to decide what that leading digit happens to be. The statistical aspect of Benford's law is not necessarily mimicked by what is happening here, but once you establish a counting system, then that's what happens. And that's a great question as to whether there's a deep physical rule to that. I hope that answers the question reasonably well. Jennifer Markham has a mantra sharing: think and act like a scientist or physicist in everyday things you do. Less screw ups, more success. I must agree with you, Jennifer. But I think what we should remember is that acting like a scientist is not necessarily what you might think. Like many people think that like a scientist is some sort of creature of rules and only almost robotic, right? If A, then B, and if B, then C, and everything is all straightforward. But that's not necessarily what thinking like a scientist is, because after all, scientists are human, right? And what humans tend to have, we think, is free will, right? Now, I'll get to that as a nice wrap up sort of to our hour and a half here today about free will and what physicists think about its existence or otherwise. But the human being who has studied science has not so much been indoctrinated in a series of facts and if-thens, right? It's more along the lines of you have been given the opportunity to learn how to look at the information that you receive, to think about it, to decide whether or not that it's true or false, and then go from there. The rational human mind is surprisingly irrational, even if you're trying to do that, right? If you're trying to be scientific. It, the human brain is just a strange and amazing physical construct. The physics of the mind is one of the last things I talk about in my frontiers of physics when I discuss that in the book. And that is that if you count up the number of neurons, brain cells in your brain, and the number of connections, the synapses and the different dendritic and axonic connections that they have with one another, you actually have more such connections in your brain than the entire observable universe has stars. So it is a very complicated system. So no matter what you try to do, you cannot limit that complicated a system into a series of steps that you must follow all the time. There's no one right answer at all times. Now, we've all heard of things like cults, right? People's Temple, where the horrific things were going on there or whatever, or people who believe in conspiracy theories and regardless of whatever evidence that they're presented with, they will still cling to it and refuse to change that. Now, a lot of times we say, oh, that's just brainwashing. Somehow our subconscious mind has been subverted. But my psychologist colleagues tell me that that's not the case. It's in fact the thinking part of our heads, the ones with the densest, the most complicated connections that actually get changed and get moved in such a position that you wind up ossified in these kinds of ideas, conspiracy theories or religious fervor or whatever, that completely is not based on facts or evidence, like faith-based knowledge as opposed to non-faith-based knowledge. That actually occurs in the cortex, in the part that we think. It's the conscious part of our brain, not the subconscious part. So the human brain changes a lot. It's very, very malleable. And that's both good and bad. Bad, perhaps, because you hold on to irrational ideas that are not good for you, some conspiracy theories, perhaps, or cult-like behavior. But on the other hand, it's a very good thing because then we can learn. right? By me talking with you now, isn't it amazing that just by hearing the things that I'm talking about, you have added new connections and information into your brain that you might not have thought of before? And that kind of change is what allows us to teach the future generations, helps them to learn how to learn. It helps us all be able to survive in the society that we're in today. And of course, it causes all kinds of headaches and difficulties in our society. But you know what? I'd rather have it this way than the other way. Right. So thinking and acting like a scientist or a physicist in everyday things you do, to me, is like looking at a light or a light switch and realizing all the cool things that are going on, the electrons and the motion and the mechanics and the force and the energy that are behind it. Or seeing all kinds of neat things happen out there. A blade of grass is so interesting. Uh, every one of us as a human being has amazing systems within us. Our digestive system, our immune system, all of it is linked together physically. And then the stars in the sky, the galaxies in the universe, they are really, really cool. And every one of them is as fascinating and as cosmic or as ordinary as we are as individuals. And that complexity and understanding how they link together give us the ability to appreciate when we get new information, how it all fits. So when we hear something on the news and we say, well, this is the proper way to behave under these circumstances, then we know, well, should we just listen or should we think about whether to listen? Does our knowledge of the universe jibe with that? And can we compare and can we make those educated, thoughtful decisions to test whether our behavior is true or false and use the evidence that we get from that to run our lives? And I think that is the best idea of how to live like a physicist, how to think like a physicist. And once again, let me just say, you are all physicists. Whether or not you've ever solved a differential equation to figure out the motion of an object in the universe, that doesn't matter. You are doing physics every day. And don't let anybody tell you otherwise, and enjoy the universe like that every day and realize that. Okay? And so I want to thank you for the time that you spent with us today. It's a real pleasure always to be able to share some of these things. I'm very, very pleased and happy that you came to hear some of these things. And if you have any further questions, we have 4 more minutes. I will answer some more, and we can just chit and chat. Feel free to take yourself off of mute if you want to ask a question, or Maurice can provide something for you. Thank you again so much. It's been a real pleasure, and the adult school is awesome. So thanks, Maurice, and thank you to everybody for being here. And I'd be happy to talk with you more as time goes on. Okay, thanks so much.
Thanks again, Charles.
Thank you, Maurice.
Thank you.
Okay.
If I could go back to that wandering magnetic poles one
For
more
sure.
time. It's like, does that have anything to do with the GPS? The
Great
magnetic
question.
poles?
As it turns out, GPS does not use electromagnetism to determine where you are. It uses geometry. So the electromagnetic field of the Earth can affect the operations of the satellites because those GPS satellites work on electricity, right? So at any given time, they could be affected and malfunction or function differently. But the magnetic field's motion won't affect the general relativistic changes that happen with the motion around Earth's gravitational field.
Huh. Thank you.
You're welcome. Yes, and Ray, let us do it again soon. Let's do all of this again soon. Well, I guess we'll just let Maurice decide when the next time was going to be, right?
Come on, Maurice.
We'll do the spring. Spring will be around the corner, so maybe April, maybe May. We'll make it happen.
Yeah,
Right.
and sooner the better that we can get back into that beautiful library and sit together and just chat and ruminate. That'll be lovely.
That'd be really nice.
Okay.
I really like that.
All right. Thank you again very much, everybody. Okay, take care. Bye now.
Take care. Thank you, everyone.
Thank you,
Have a
Maurice.
good night.
Good night, everyone.